Hi, this is Lance from LangChain. I want to talk about a pretty fun analysis that I've been working on for the last few days, called multi-needle in a haystack. Um, and we're going to talk through these graphs and what they mean and some of the major insights that came out of this analysis. But first I want to kind of set the stage. So context lengths for LLMs have been increasing. Most notably, Gemini 1.5 and Claude 3 have recently reported up to 1 million token context lengths. And this has provoked a lot of questions. Like if you have 1 million tokens, which is hundreds or maybe thousands of pages, can you replace RAG altogether? Why would you need an external retrieval system if you can plumb huge amounts of context directly into these LLMs? So it's a really good question and a really interesting debate. To help kind of address this, Greg Cameron recently put out an analysis called Needle and Haystack, which attempts to answer the question, how well can these LLMs retrieve specific facts from their context with respect to things like how long the context is or where the fact is placed within the context? So he did a pretty influential analysis on GPT-4 and also Claude, which basically tested along the X are different context lengths. So going from 1K all the way up to 120K in the case of GPT-4, and on the Y being different document placements or fact placements within the document. So either put it at the start of the doc or put it at the end. So he basically injects this needle into the context at different places and varies the context length, and each time asks the question that you need the fact or the needle to answer, and basically scores it. Can the LLM get it right or wrong? And what he's found is that the LLM, at least in this case, GPT-4, fails to retrieve facts towards the start of documents in the regime of longer context. So that was kind of the punchline. It's pretty interesting. It's a nice way to characterize performance of retrieval with respect to these two important parameters. But, for RAG, you really want to retrieve multiple facts. So this was testing single fact retrieval, but typically for RAG systems, you're chunking a document, you're retrieving some number of chunks, maybe 3 to 5, and you can do this reasoning over disparate parts of a document using similarity search and chunk retrieval. So kind of to map the idea of RAG onto this approach, you really would need to be able to retrieve various facts from a context. So it's maybe like 3 needles, 5 needles, 10 needles. And Google recently reported 100 needle retrieval. So what they're showing here is the ability to retrieve 100 unique needles in a single turn with Gemini 1.5, and they test a large number of points here. They vary the context length, you can see on the X, and they show the recall, their number of needles that they return on the Y. Now, this kind of analysis is really interesting because if we're really talking about the ability to kind of remove RAG from our workflows and rely strictly on context stuffing, we really need to know, what is the retrieval, recall with respect to the context length or number of needles? Does this really work well? What are the pitfalls, right? So I recently added the ability to do multi-needle retrieval and evaluation to Greg's open source repo. So Greg open sourced this whole analysis. And what I did is I went ahead and added the ability to inject multiple needles in a context and characterize and evaluate the performance. So the flow is laid out here. It's pretty simple. And all you need is actually 3 things. So you need, try to just move this over. So you need a question. You need to know your needles. You need to have an answer. So that's kind of the way this is structured. So a fun toy question, which is kind of derived from an interesting Claude 3 needle in a haystack analysis, is related to pizza ingredients. So they reported some funny results with Claude basically trying to find a needle related to pizza ingredients in a sea of other context. And Claude 3 kind of recognized it was being tested. It was kind of a funny tweet that went around. But it's actually kind of a fun challenge. We can actually take the question, which was, what are the secret ingredients needed to build the perfect pizza? And the answer, the secret ingredients are figs, prosciutto, and goat cheese. And we can just parse that out into 3 separate needles. So our first needle is figs, are the secret ingredients. The second needle is prosciutto. The third needle is goat cheese. Now, the way this analysis works is we take those needles and we basically partition them into the context at different locations. So we basically pick placement of the first needle, and the other 2 are then allocated accordingly into kind of roughly equal spacing. depending on how much context is left after you place the first one. So that's kind of the way it works. Um, you then pass that context to an LLM along with a question, have the LLM answer the question given the context, and then we evaluate. In this toy example, the answer only contains figs, and evaluation returns a score of 1 for figs and also tells us which needle it retrieved spatially. So that's the overall flow, and that's really what goes on when you run this analysis based on the stuff that I added to Greg's repo. Um, now, um, if we want to set this up, another thing I add to the repo is the ability to use LangSmith as your evaluator. And this has a lot of nice properties. It allows you to log all of your runs, it orchestrates the evaluation for you, and it's really good for auditing, which we can see here in a minute. So I'm going to go ahead and create a LangSmith dataset to show how this works. And all you need is, so here's a notebook. I've just set a few different secrets or environment variables for like LangSmith API key, LangChain endpoint, and tracing v2. So basically set these, and these are done in your LangSmith setup. And once you've done this, you're all set to go. So if you go over then to your LangSmith kind of overall project page, it'll look something like this, where you can see over here on the left, you have projects, annotation queues, deployments, data sets and testing. And what we're going to do is we're going to go to data sets and testing. And what we're going to do here is we're going to say create a new data set. I'll move this down here. And we're going to create a new data set that contains our question and our answer. And we're going to call this multi-needle test. So here we go. We'll call this multi-needle testing. We'll create a key value data set and just say create. So now you can see we've created a new data set. It's empty. It has no tests and no examples. And what we're going to do is we're going to say add example here. And what we're going to do is just copy over our question. There we go. We'll copy over that answer. So again, our question is, what are the secret ingredients needed to build the perfect pizza? Our answer contains those secret ingredients. We submit that. So now we have an example. So this is basically a data set with one example, question answer pair. No tests yet. So that's kind of step one. Now, all we need to do simply is, I've already done this. So if we go up here, so this is Greg's repo. You need to clone this. You need to just follow these commands to clone, setup, create a virtual environment, pip install a few things, and then you're set to go. So basically all we've done is set up LangSmith, set these environment variables, clone the repo. That's it. Create a data set. We're ready to go. So if we go back, this is the command that we can use to run our evaluation. And it's a few pieces. So we use LangSmith as our evaluator. We set some number of context length intervals to test. So in this case, I'm going to run 3 tests. And we can set our context lengths minimum and our maximum. So I'm going to say I'm going to go from 1,000 tokens all the way up to 120,000 tokens. And 3 intervals, so we'll do basically 1 data point in the middle. I'm going to set this document depth %min is the initial point at which I insert the first needle. And then the other 2 will be set accordingly in equal spacing in the remaining context. That's kind of all that you need there. We'll use OpenAI. I'll set the model I want to test. I'm going to basically flag multi-needle evaluation to be true. And here's where I'm basically going to point to this data set that we just created, this multi-needle test data set. I specified here in this eval set. And the final thing is I just say, here's the 3 needles I want to inject into the context. And you can see that maps exactly to what we had here. We had our question, our answer, those are in LangSmith, and our needles we just pass in. So that's really it. We can take this command and I can go over to, so here we go. So I'm in a fork of Greg's repo right now. And I'm just going to go ahead and run. So we should see this go ahead and kick off. It has some nice logging. So it shows like, okay, here's like our experiment. Here's like what we're testing. Here's the needles that we're injecting. Here's where we insert in the needles, and this is like our first experiment with 1,000 tokens, and it's just rolling through these parameters. So it rolls through the experiments as we've just laid out, and what we can see is if we go over to LangSmith now, we're going to start to see experiments or tests roll in. That's pretty nice. And what we can do is we can kind of select here different settings we want to look at. So if you want to look at needles retrieved, for example, we can see those scores here. Now this final one's still running, which is fine. But it's all here for us. And let's try to refresh that. Okay, so now we have them all. So this is pretty cool. You can see how much it cost. So again, be careful here. At 120,000 tokens, it costs about $1. So it's expensive. But smaller contexts, very cheap, right? So your price per token. You can see the latencies here, the P99, you can see the P50 latency, creation time, runs. And what's kind of cool is you can see everything about the experiments logged here. The needles retrieved, the context length, the first needle depth percentage, the insertion percentages, model name, the needles, number of needles total. So it's all there for you. Now I'm going to show you something that's pretty cool. You can click on one of these and it actually opens up the run. And here you can see here was like our input, here was the reference, or here was the input, here's like the reference output. This is like the correct answer. And here's what the LLM actually said. So in this case, it looks like the secret ingredients need to build the perfect pizza include prosciutto, goat cheese, and figs. So it gets it right. And you can see it scores as 3, which is exactly right. So that's pretty cool. Let's look at another one. So we can look at this is our 60,000 token experiment. So it's the one in the middle. And in this case, you can see the secret ingredients need to build the perfect pizza are goat cheese and prosciutto. So it's missing figs. So that's kind of interesting. And we can see it correctly scores it as 2. Now we can even go further. We can actually open this run. And you can see over here, this is just the trace. This is kind of everything that happened. We can look at our prompt. And this is like everything in our prompt. Now what's pretty nice is we can actually see right here, this is the entire prompt that went into the LLM. And here is the answer. Now what I like about this is if we want to verify that all the needles were actually present, so we can actually just search for like secret ingredient, right? You can see figs are one of the secret ingredients. So it's in there. It's definitely in the context. It's not in the answer. We can just keep searching. So prosciutto, goat cheese. We can see all 3 secret ingredients are in the context and 2 are in the generation. So it's a nice sanity check to say, okay, the needles are actually there. They're where you expect them to be. I find that very useful for auditing and making sure that the needles were actually placed correctly. So it's really nice to be able to do that to kind of convince yourself that everything's working as expected. So what's pretty cool then is when I've done this, I actually can do a bit more. So I'm just going to copy over some code here, and this will all be made public. So I'm just paste this into my notebook, and what this is going to do, this is basically just going to grab my data sets. I just pass in my eval set name. It's going to suck in the data that we just ran, and I think that's probably done. We can have a look. Yep. So you can see, nice. It loads this as a pandas data frame. It has all this, all this run information that we want. It has the needles. And what's really nice is actually it has also the run URL. So this is now a public link that can be shared. And you can share those with anyone. So anyone can go ahead and audit this run and convince themselves that it was doing the right thing. So with all this, we can actually do quite a lot. And we've actually done kind of a more involved study that I want to talk about a little bit right now. So with this tooling in place, we're able to ask some interesting questions. We focus on GPT-4 to start, and we kind of just talk through usage. This is a blog post that'll go out tomorrow along with this video. We talk through usage, so I don't want to cover that too much. We talk through workflow. But here's like the crux of the analysis that we did. So we set up 3 eval sets for 1, 3, and 10 needles. And what we did is we ran a bunch of trials. We burned a fair number of tokens on this analysis, but it was worth it because it's pretty interesting. What we did is test the ability for GPT-4 to retrieve needles with respect to like the number of needles and also the context length. So you can see here is what we're doing is we're asking GPT-4 to retrieve either 1, 3, or 10 needles. Again, these are pizza ingredients in a single turn. And what you can see is with one needle, um, whether it's 1,000 tokens or 120,000 tokens, retrieval is quite good. So if you place a single needle, not a problem. Now, I should note that this needle is placed in the middle of the context, which may be relevant, but at least for this study, the single needle case is right in the middle, and it's able to get that every time, regardless of the context. But here's where things get a bit interesting. If we bump up the number of needles, so for example, look at 3 needles or 10 needles, you can see the performance start to degrade quite a lot when we bump up the context. So retrieving 3 needles out of 120,000 tokens, you see performance drop to like, around 80% of the needles are retrieved. And it drops to more like 60% if you go to 10 needles. So there's an effect that happens as you add more needles in the long context regime, you miss more and more of them. And that's kind of interesting. So because we have all the logging for every insertion point of each needle, we can also ask, like, where are these failures actually occurring? And this actually shows it right here. So what's kind of an interesting result is that we found, here's an example of retrieving 10 needles at different context sizes. So on the X here, you can see the context length going from 1,000 tokens up to 120,000 tokens. And on the Y here, you can see each of our needles. So this is the start of the document up at the top. So needle 1, 2, down to 10 are inserted in our document at different locations. And each one of these is like one experiment. So at 1,000 tokens, you ask the LLM to retrieve all 10 needles, and it gets them all. You can see this green means 100% retrieval. And what happens is, as you increase the context window, you start to see a real degradation in performance. Now, that shouldn't be surprising. We already know that from up here. That's the case, right? Getting 10 needles from 120,000 is a lot worse than getting from 1,000. 1,000, you get them every time. 120,000 is 60%. But what's interesting is this heat map tells you where they're failing, and there's a real pattern there. The degradation in performance is actually due to needles placed towards the top of the document. So that's an interesting result. It appears that needles placed earlier in the context have a lower chance of being remembered or retrieved. Now, this is a result that Greg also saw in the single needle case, and it appears to carry over to the multi-needle case, and it actually starts a bit earlier in terms of context sizes. So you can think about it like this. If you have a document and you have like 3 different facts you want to retrieve to answer a question, you're more likely to get the facts retrieved from the latter half of the document than the first. So it can kind of like forget about the first part of the document or the fact in the first part of the document, which is very important because, of course, valuable information is present in the earlier stages of the document, but we may or may not be able to retrieve it. The likelihood of retrieval drops a lot as you move into this kind of earlier part of the document. So anyway, that's an interesting result. It kind of follows what Greg reported for the single needle case as well. Now, a final thing we show is that oftentimes you don't just want to retrieve, you also want to do some reasoning. So we built a second set of eval challenges that ask for the first letter of every ingredient. So you have to retrieve and also reason to return the first letter of every secret ingredient. And what we found here is basically that green is reasoning, red is retrieval, and this is all done at 120,000 tokens. As you bump up the number of needles, you can basically see that both get worse, as you would expect, and reasoning lags retrieval a bit, which is also what you kind of would expect. Retrieval kind of sets an upper bound on your ability to reason. So again, it's important to recognize that 1, retrieval is not guaranteed, and 2, reasoning may degrade a little bit relative to retrieval. So those are kind of the 2 points that are really important to recognize. Um, and maybe I'll just like kind of underscore some of the main observations here. And, especially as we think about long contexts more, we think about replacing RAG in certain use cases. It's very important to understand the limitations of long context retrieval, and like, multi-needle retrieval from long context in particular. There's no retrieval guarantees. So multiple facts are not guaranteed to be retrieved, especially as the number of needles and the context size increases. We saw that pretty clearly. And there can be different patterns of retrieval failure. So GPT-4 tends to retrieve needles, tends to fail in retrieval of needles towards the start of the document as the context length increases. That's point 2. Point 3 is prompting may definitely matter here. So I don't presume to say we have the ideal prompt. I was using kind of the prompt that Greg already had in the repo. It absolutely may be the case that improved prompting is necessary. There's been some evidence that you need that for Claude, so that's like very valid to consider. And also that retrieval and reasoning are both very important tasks, and retrieval might kind of set a bound on your ability to reason. And so if you have a challenge that requires reasoning on top of retrieval, you're kind of like stacking two problems on one another, and your ability to reason may or may not be kind of governed or limited by your ability to retrieve the facts, which is pretty intuitive. But, it's just a good thing to underscore that like reasoning and retrieval are kind of independent problems, and retrieval is like a precondition to reason well. Those are the main things I want to leave you with. I also will have a quick note here that if we go back to our data set, which we can see here, like how much did this actually cost? I know people are kind of worried about that. So just the 3 tests that we did are around, maybe around $2. So again, it's really those long context tests that are quite costly. LangSmith shows you the cost here, so you can actually track it pretty carefully. But the nice thing is, for like a kind of well-designed study, you could spend maybe $10 and you could actually look at, quite a number of trials, especially if you care more about like the middle context length regime. You can do quite a number of tests within a reasonable budget, So I just want to throw that out there that you don't necessarily have to totally break the bank to do some interesting work here. The things we did were pretty costly, but that was mostly because we generated a large number of replicates just to validate the results. But if you're doing it for yourself, you could do it as just a single pass. And this is actually not that many measurements, So here it would be like 1, 2, 3, 4, 6 measurements if you don't do any replicates. So, it's not too costly to produce some interesting results using this approach. Everything's open source. All the data is open source as well. It's all checked into Greg's repo. You can find it in the Viz section, and multi-needle data sets. It'll all be there. So yeah, I encourage you to play with this. Hopefully it's useful, and I think long context LLMs are super promising and interesting. And analysis like this hopefully will make them at least a little bit more understandable and build some intuition as to whether or not you can use them to actually replace RAG or not. So thanks very much.